this is that exponential problem, number 13, I think. And this is the setup. We have, and you can tell exponential, that, by the way, and also, was it number 11? When you have like a growth rate that's established, a consistent growth rate, that is a red flag for exponential. And so that number 11 you guys didn't ask about, but you should know if you look on your test, that one is, does anyone want their test? You guys want to look at it right now? Some of you gave them to me. Come and get it if you want to look at this. And if you're not wanting to look at it, don't come and get it. But next part. Okay, fast. This says half-life. How long until you get half of your substance? And if you're asking for how much long until you get half, that means my initial value, I know it's not written in there, but that initial value, that y naught that's written in there, is, say, 10. I want to know when I have half of that, like 5. If I solve by dividing both sides by y naught, I always get 1/2 equals, e to the negative 1.2t. So half-life problems always start out the same way. 1/2 equal to the exponential portion of it, log of both sides, nothing fancy there. That allows us to pull out the 1.2, log of e is 1, divided by negative 1.2, and we're home free. So that's all it's asking. Now there might be other weird confusions. I know the algebra is easy for you guys. So what do you think? Is that cool? Half-life problems, when do you have half? So you take, and you can make up any initial value you want. You just have to find out when you get half of it. So exponential decay is kind of uniform regardless of how much you start with, which I still think is interesting because it's decaying regardless of surface area or mass. Just decays at the same rate no matter what. So that's 13. Now, part B of that question is, when do I lose 98% of it? And if I lose 98%, that means I am resulting in 2% of the actual original mass. So when do I end with 0.02? So it takes a little while, but it's an inversion of, if I want to know when I've lost 98%, that means that I get down to 0.02 of the original. It doesn't matter what you start with. If you make y, like your initial value, 100, then I want to know when I get back down to 2. If I divide both sides by 100, I get 0.02, regardless of what you start with initially. So that's the equation. Log both sides, divide, solve. Does that seem straightforward? Pretty good?
There's just so much math.
Okay. What's that?
I want to try calculus 3.
You should.
No, I want to do a problem in here one day.
I thought Calc 3 was easier than Calc 2. But,
Really?
yeah.
Yesterday, Calc 3 was impossible.
Really?
Yeah.
I must have been the guy I had. He was this crazy, he was an interesting Russian fella. But it sure seemed easy at the time. So I don't know. Maybe he just made it easy. 14. V naught. It adds a third dimension. It's all the same rules though. V and V naught. It's exponential. Like it's this stopping bus or stopping vehicle that weighs a lot of. And we decided it was hard to decide what the K and the M all stood for. It turns out the little m is mass. K is given. So you fill it all in with the mass of the vehicle. An initial velocity of 20. 1200, I don't know, I guess I forgot what it's measured in, I don't have it in front of me, but there's 80 was given as K. So once you fill all the elements in, then you have an equation. It says, hey, when does this thing stop? When is the velocity 0? And theoretically, an exponential decay never hits 0. So it hits 0 when time is infinity. And that sounds ridiculous, but we found out you can stop. You can find out when it stops, even though it stops when time is infinity. It's doable. And there's some notation I didn't show you guys. So even if you're working on something else and you're checking out for a second because you got this, I want to show you notation. So watch carefully. What I showed you the other day by putting in infinity is not technically correct. The technical way to write it is you have to write it with limits. So for this instance, here's the problem. I'm going to integrate because the question is how far until it stops. And what I'm going to do is integrate from 0 to infinity because that's the time when it stops. Now last time I put in infinity, this time I'm going to put a variable instead. I'm just going to clean up the integral a little bit first. You know we're integrating from 0 to this infinity. And the way we're going to notate, and we're going to take the antiderivative. So all this is all peach keen. That's the antiderivative. But now with that notation, here's how you write it. And it's in red, and it's barely readable. I'm going to use a as the upper bound instead of infinity. And I'm going to do the limit as a goes to infinity. It basically implies the same thing. I'm using infinity as my upper bound. But the proper notation is to say the limit as a goes to infinity of 0 to a, rather than just doing an integral from 0 to infinity. Small little detail. Not a conceptual requirement, but a necessary notation requirement. So that just means all of these, as you write them, this is how it gets written out. Instead of plugging in infinity directly like we did before into the antiderivative, and by the way, 20 times negative 15, I just distributed, got the negative 300. But every time you would want to put in that a, you want to accompany it with that limit as a goes to infinity. And it's like plugging in infinity. You can directly substitute it in there. So this part we're going to play with later. So as we get down to some free response questions later that have these in it, these indefinite integrals, then we're going to have to keep track of anytime we have the inclination to plug in an infinite value for a bound in our integral, we have to use limit notation. We can't put in infinity directly. And that's all. That's the story on those. So that is the limit as a goes to infinity is part of the antiderivative. It's part of where I substitute a into that function on the, for my upper bound, there's that limit as a goes to infinity of e to the negative 1/15 a. So that's it. That's the story. And then we evaluate, so I'll keep rolling. So you get 0, because e to the negative 1/15, as a goes to infinity, we know this gets to 0. Limits allow you to go places that you usually can't go. Isn't that fun? We get 300. 300. It stops in 300 meters, even though it technically never stops. It's one of the great concepts of integral calculus. This thing is never going to stop, except in 300 meters. You can have any color you want, says Henry Ford, as long as it's black. And apparently that's why the Dodge brothers broke off. I don't know, you guys saw the commercial about the Dodge brothers? Yeah, they started their own car company because they wanted to do cars differently.
So, Mr. Seeley, are you going to create your own